So the first lens we have here is a diopter flatter than K. Remember, our K readings are 42 by 44 at 90. Got a 41 diopter lens on the eye. And when we click on this video, you can see that the center of the lens is coming in contact with the center of the cornea. And what happens is that the lens displaces laterally. So one time it goes temporally, sometimes it goes nasally. But after the patient blinks and gravity pulls the lens away from the upper lid, the lens will displace to one side or the other. This is obviously not an ideal fitting relationship. Now when we look at a lens that is a 42 diopter base curve, which is exactly on flat K in this particular instance, you can see our simulated fluorescein pattern shows 20 microns of clearance. And when we fire up this video, you can see that when the patient blinks, the lid pulls the lens up, gravity pulls the lens down away from the lid. Because the lens is coming in contact at 3 and 9 o'clock, it keeps the lens centered along the horizontal axis. And you can see how nicely that lens centers, after each blink. So this is what we would consider a nearly ideal fit. And you can see those touch points at 3 and 9 o'clock out where the optical zone comes to an end and the peripheral curve system begins. But really an ideal fitting relationship in this particular case, which happened to be on flat K. Now the second GP fitting factor we need to look at is that there should be a mid-peripheral contact point along the horizontal meridian. And this just very simply means that we're clearing the center of the cornea. As the lens comes down on the eye, the contact point should be at 9 o'clock and 3 o'clock, and that'll keep the lens from moving laterally along the horizontal axis. And with our 18 microns of clearance, remember the ideal number being between 10 and 20, you can see those contact points where the fluorescein thins out, the lens comes in contact with the eye here at 9 o'clock and over here at 3 o'clock. This would be considered an ideal fluorescein pattern. And in this case, we would expect, for a very well-centered contact lens. Now, what makes this a little bit tricky is that the contact points in the periphery, depending on the eccentricity of the eye, can vary rather dramatically. So most of us have been taught to fit rigid lenses using central keratometric readings. And this just shows you maybe one of the built-in flaws of using a keratometer to fit rigid lenses. Not that it can't be done, but why it may be a little challenging on some patients more than others. Let's look at 3 patients with different eccentricity values. Well, patient 1 here has an eccentricity value of 0.20, so the cornea is much steeper in the mid-periphery. The second patient has a value of 0.40, kind of a more normal eccentricity value. And then finally one with a 0.6 value. When we put a 42 diopter lens on each of these 3 patients, it'll fit ideally on one of them, and in this case the 0.40. But in the other 2 eccentricity values, we're going to have a lens that's either too flat or too steep. So ideally, if we could measure the cornea in the periphery where the lens comes in contact with the eye instead of in the center where we want it to actually clear the central cornea, we may have some more valuable information. And what we've found with like the 9.5 CAD design, if we go out 1, 2, 3 millimeters temporally and determine this point on our topographer on the axial map, we have a very good starting point for what the base curve should be for our 9.5 diameter lens. And it's just a very simple way for those of you that have topography to kind of get a good starting point in your diagnostic fitting. Again, it certainly can be done using the flat K on central keratometry, just a little bit more accurate when you have peripheral topography to work with. Now the final GP fitting factor that I want you to consider is that the lens should maintain unobstructed movement along the vertical meridian. And it's what we call unobstructed vertical movement, basically. And it just means that the lens is not impinging along the vertical axis of the eye. So as the patient blinks, we want the lens to be picked up by the lid, move freely along that vertical position to keep from it, rubbing against the cornea and causing discomfort. When we do see a patient wearing a contact lens that has restricted movement along the vertical axis, we find that they're usually uncomfortable around 4 hours of wearing time. So the cornea can only maintain comfortable wear for about 4 hours when there's impingement somewhere along that axis. And it's simply because the patient's blinking so many times during the day that lens just cannot take the drag, just the mechanical rub of the lens against the cornea. So we really want freedom of movement. From a topography standpoint, when we're designing these lenses using a topographer, we're looking for about 40 microns of clearance here in this position right here where the lens is up off the eye, about 40 microns. So we're going to expect to see a little brighter fluorescein pattern at 6 o'clock and 12 o'clock than certainly we would at 3 o'clock and 9 o'clock, or even in the center of the lens. So, it's a very simple system where we're looking for the lens to clear the center of the cornea, have bearing points at 3 and 9 o'clock, and clear the cornea freely at 6 and 12 o'clock. Now, the ideal person for doing this on is a patient with width-of-rule astigmatism. Patients with astigmatism, fortunately for us, most of them have width-of-rule astigmatism, are really ideal fits with rigid gas permeable lenses. You can see what this map allows us to really preview is that the lens is going to come in contact with the cornea where the cornea is the flattest in the mid-periphery. It's going to be loosest or come off the eye the most where the cornea is the steepest. In this patient with width-of-rule astigmatism, we've got touch points at 9 o'clock and 3 o'clock, clearance points at 12 o'clock and 6 o'clock. And looking at this, we would expect a successful fit with a spherical rigid gas permeable lens. We have that unobstructed vertical movement. We're clearing the central cornea, and we've got touch points at 3 and 9 o'clock, and we would just expect this to be a very successful outcome. Let's look at an example of a patient with K readings of approximately 4175 by 4375. So we've got about 2 diopters of width-of-rule astigmatism. We've got a flat K of approximately 4175. And you can see, just looking at the map, because we're flat out here in the mid-periphery at both 9 o'clock and 3 o'clock, we expect our touch points there. We expect unobstructed movement along that vertical axis, and we can start our design. Now, again, if you don't have a topographer, you're going to be using diagnostic lenses to do this. But if we put a 4175 on this particular patient, because of the eccentricity of the eye, you can see that the center of the lens is touching. It's very flat. So we can visualize this on the topographer and say we probably need to go steeper than 4175. If we do put a 4175 on, there's likelihood that it's going to touch in the center. And let's go through the process of taking a look at that. So we've got our 4175 lens on the eye. See if we can start up the video. When the patient blinks, the lens comes up with the lid as it should. But as the lens is gravity induced down, we can see that it tends to move laterally left and right. So in this particular case, we've got a lens that's too flat, and typical of a flat lens, the lens is riding high. Now when we go with a lens that's a half a diopter steeper than K, our simulated fluorescein pattern is represented with about 20 microns of clearance in the center, about just over 40 microns of clearance out in the periphery along the vertical axis. And when we look at that lens on eye, and unfortunately this is not a video, but when we look at that lens on eye, you can see the touch points again at 9 o'clock and 3 o'clock. And you can see how well that lens is centered, and you can appreciate that there is no touch here in the center. There's touch here in the mid-periphery, but it's clearing the center of the cornea to a point of about 20 microns of clearance, and we would expect that to be a very, very successful fit. Now let's go one step further and create a lens with a base curve of 4275, which would be considered a diopter steeper than K, and maybe just a little, half a diopter steeper than the last lens we looked at. You can see now that we're clearing the cornea in the center more than 20 microns. We're still just over 40 microns out here in the periphery, So we should still be okay there. And when we look at this lens on eye, this 1 diopter steeper than K lens on eye, you can see that there's a significant amount of pooling in the center of this contact lens. So let's run this video and see what happens. Now the lens is still picked up, drops pretty rapidly though into place. That's because of the impingement up here above. We've got a little more impingement than we had at a half a diopter steeper than K. We've got more tear film than we need in the center of the lens, and we probably are running the risk of 3 and 9 staining that could lead into vascularized limbal keratitis or VLK, and I would consider this a slightly steeper lens than what we'd necessarily need. Still centers well, probably could be considered a successful fit, more chance for lens flexure, little more tear film than we need under the center, little more risk of 3 and 9 o'clock staining. Not an ideal fit, but not a terrible fit. And then finally, once we've determined our diameter first, our base curve second, we need to determine the power of the lens. And we certainly do this most of the time with just a simple spherical over refraction. But oftentimes we can use, if we're doing empirical fitting especially, the old SAMFAP rule. SAMFAP basically says if the base curve of the lens is steeper than the patient's flat K, we're going to add minus power, an equal amount of minus power. For every quarter of a diopter we are steeper than flat K, we're going to add a quarter diopter more minus. And we're going to add plus if the lens is flatter. So if the base curve of the lens is flatter than the patient's flat K, we're going to be adding plus, the basic SAMFAP rule. Now, my intention is to do a series of these webinars where we're talking about bi-toric design, we're talking about keratoconus designs, reverse geometry designs, multifocal designs. So I really appreciate Josh and Janice's support with this at Valley Contax, and hopefully you'll follow along as we kind of walk through step by step how to design some of these more complex fits. I appreciate that you took the time to listen to this, and I want to wish you the best of luck in designing and working with rigid lenses, and hopefully I've convinced you that this is a very viable option for your practice and your patients. Thank you very much.